Last up for the Pollard row section, I want to talk about how Pollard row can be used to calculate discrete logs. So just a reminder here, when you're computing a discrete log, you're given a prime p, a primitive root mod p, and some x that's not 0 mod p. And then your goal is to solve the equation g to the k is x mod p. And this, it turns out, is a rather difficult equation to solve. And our goal with the Pollard row discrete log algorithm is actually going to be to generate a much simpler equation that we can solve instead. But before I get into that, I want to remind you what the baseline is. That is to say, what would be the running time if I were to use the sort of naive algorithm here? And so the naive algorithm here is to calculate g to the 1, g squared, g cubed, g to the 4th, etc., until x is found. So basically, this is guess and check. I guess a k, see if it works. If it doesn't, try another k until I get there. There are p minus 1 possible values of k. And so, on average, I'll succeed after trying half of them. And so the number of steps I expect here is roughly p over 2, but ultimately the point is this is O of p. Our goal here with the Pollard row discrete log algorithm is to chop this down from O of p to O of square root of p. And we're going to do that by looking for a particular kind of collision. And what kind of collision is it we're going to look for? I'm going to calculate g to the a times x to the b for lots of pairs a and b. And I'm going to do this until I find two different times where this number is the same value. I'm going to call this number y. So that is, I'm looking for two different pairs, a and b, that give me the same value of y. So what that's going to look like is g to the a1 times x to the b1 is equal to g to the a2 times x to the b2 mod p. Now, if I find this, how does that actually help me? Well, let's remember that the thing I'm trying to find is k, and that x is g to the k. So I'm going to replace these x's in this equation with k's. So that is to say this equation will become g to the a1 times g to the k to the b1 is equal to g to the a2 times g to the k to the b2 mod p. Doing a little bit with exponents, this gets us g to the a1 plus b1 times k is congruent to g to the a2 plus b2 times k. Now, remember this g is a primitive root, which means that the exponents here effectively have period p minus 1, because remember, a primitive root is something where the period of g to the x is p minus 1. So I can actually say if these two numbers are equal mod p, their exponents are actually congruent mod p minus 1. And so, remember I said the goal here was to generate an easier to solve congruence. This one involves an exponent, and so that's what made this difficult. I was trying to solve for the exponent. In this congruence, this is now just a linear congruence, so I can solve this in our usual fashion. So I'm going to move the k stuff over there, the a stuff over here, so this will end up looking like b1 minus b2 times k is congruent to a2 minus a1 mod p minus 1. And so this is a much easier equation to solve. Now, you might be inclined to say, oh, well, just multiply by the inverse of b1 minus b2, and then you're done. And if b1 minus b2 has an inverse, that will definitely work. But note we're now working mod p minus 1, where lots of things don't have inverses. For example, every even number will not have an inverse. And so we might have to do something slightly more subtle when it comes to solving this last equation. But that's our goal. Finding our repeats of values of y, that is, values of some power of g times some power of x, just naturally sort of spills out into giving me this kind of linear equation, which I can then solve using methods we already know. So now let's give an outline of how we're actually going to do this. So to initialize, we're going to pick a random a and b to start with. And these things are exponents of something mod p, so they're effectively working mod p minus 1 anyway, so I might as well pick something that's between 1 and p minus 2. And then I'm going to use those to calculate my y0, which is going to be g to the a0 times x to the b0. Now I'm going to have to define my function f, and I'm going to go ahead and define my function f, and I'll just write down a function here for you that will usually work. If somehow this fails, you might need to tweak this slightly, but most of the time you'll be able to do this. So if I input a particular y, what y do I get out? So it's going to be based on y mod 3. Now, note, it's really weird to ask what y is mod 3, because y is something, again, that's living in the mod p world. And so the mod p world does not have mod 3 as a supported operation. In fact, actually, you'll notice if you go to implement this in Sage yourself, that when you try and take a mod p number, mod 3, Sage yells at you and tells you you're not supposed to do that. Remember, I can only take a mod n number, mod some other modulus m, if m actually divides n. But in this case, I'm working mod a prime, so there are no numbers that divide the prime that I could work mod. So in other words, what I've just argued for you is that what I'm about to do is complete nonsense. But I would argue, in light of what the function here is trying to do in the Pollard row algorithm, actually the fact that this is nonsense is good, because it means that I'm unlikely to stumble upon some sort of hidden structure in the mod p world where I'm working. And so instead, because this is, again, nonsense, it's more likely to generate something random, arbitrary, in terms of the path that I'm going to lay out. So I'll go ahead and write down what I'm going to do. So if y is 0 mod 3, I'll multiply by g. If y is 1 mod 3, I'll multiply by x. And if y is 2 mod 3, I'll square y. Now, as soon as I've chosen my y0 and my f, I've now got this path. And I'm going to be looking for times along this path where I get a repeat. But remember, ultimately what I'm looking for is a repeat in terms of the a's and b's. And so what that means is I actually have to keep track below the pebble or stone or whatever that you're walking along. I need to keep track of what the a's and b's are. So the reason for this peculiar looking function is that no matter which outcome I get, I know what it does to the a and b that were on the previous step. So if I'm somewhere that's 0 mod 3, and I multiply by g, what does that do? Well, that turns a comma b into a plus 1 comma b. Because all I've done is multiply by g, and remember, y is g to the a times x to the b, so if I multiply by g, that gives me one more g, so I go from g to the a to g to the a plus 1. If I instead multiply by x, well, it's the same thing, except instead of increasing a by 1, I increase b by 1. And if I square y, well, that is going to double a and b. And so the reason for this f, in addition to the fact that this f is sort of arbitrary nonsensical, is that every step you take down the path, you can keep track of what a and b are. So with y1, you'll also know what a1 and b1 are, and you'll also know what a2 and b2 are, and also know what a3 and b3 are, and so on down the line. Again, the only supported operations are add 1 to a, add 1 to b, and double a and b. Just in case you're concerned, remember that a and b can both be thought of as living mod p minus 1. And so this doubling is never going to result in some ridiculously huge number as long as you remember to reflect that in your code. Now, as always, the majority of the work is in establishing what our path is going to look like, because once we know what our path looks like, we know how to send our turtle and rabbit down the path in order to find the repeats. Namely, we'll move the turtle 1 step forward, then we'll move the rabbit 2 steps forward, then we'll ask the turtle and the rabbit what numbers they're looking at. If they're looking at the same number, then we stop. Otherwise, we repeat. So this is, again, exactly the same Pollard row algorithm we've been using the whole time. Lay out the path, send the turtle and rabbit down the path, and every time they move, ask them if they found a collision, and if not, have them keep going until they find one. So when we found this collision, what we found is 2 y's that are the same and matching a's and b's for them. So I'm going to call them AT for A turtle, BT for B turtle, and AR for A rabbit, BR for B rabbit, such that, and so the key thing here is that we have exactly the kind of thing I outlined at the beginning, which is that G to the AT times X to the BT is congruent to G to the AR times X to the BR mod P. So we have found such a coincidence. And just to remind you, we worked out the algebra of how this works out already. Namely, this is going to give us this equation for K. Now, this is really useful, except there's one bad case that can happen. Namely, there's one really obvious way for it to be the case that AT, BT, and AR, BR have this property. Namely, it could be the case that AT is equal to AR and BT is equal to BR. In that case, this equation we've just found says 0 equals 0 mod P minus 1. And that, unfortunately, is not a helpful equation to solve for K. So, just like in Pollard row for factoring, there is a rare but real fail case here. So, if this happens, we have to go back to the start and try again. But as long as this didn't happen, then we now have a real equation over here that we can solve for K. Now, again, what I want to do to solve for K is just multiply by the inverse of this number. But this number might not have an inverse, mod P minus 1. So to figure that out, I'm going to calculate the GCD of this coefficient of K and P minus 1. And I'm going to call that number D. So if this GCD happens to be 1, great, we just multiply by the inverse and we're done. This is the best possible outcome. We just literally solve exactly for what K is. Remember, K is only actually defined mod P minus 1, because again, it's an exponent mod P. Otherwise, what's going on is we have here a congruence where there's some number that divides BT minus BR, AR minus AT, and P minus 1. So we have some situation that looks something like this, where there's actually a number, in this case 4, that divides not just both of these terms, but also the modulus. And here's an operation that we've not done before, but that you can convince yourself you can do. If some number divides all of these pieces, you can actually divide all 3 of them by that number. So in this case, I'm going to divide 8, 4, and 12 by 4. And note, I'm dividing the integers 8, 4, and 12 by 4, because again, I can't divide by 4 mod 12. But what that will give me is that 2t is congruent to 1 mod 3. So why is this true? Why is it that I can divide all of these things like this? So let's say I'm solving c times t is congruent to e mod n. Let's just write out what that means. That means that c times t minus e is equal to n times, let's say, L, because it says n divides the difference, so that says the difference is n times L for some L. And so let's say all 3 of these things are divisible by d. That is, c, e, and n are all divisible by d. Then we would have c over d times t minus e over d is equal to n over d times L. And note, this is a literal equation of integers, even though there's these fractions floating around that make it look like this is not an equation of integers. it still is actually an equation of integers. Again, it looks really upsetting that I divided by d when I'm talking about modular arithmetic, which you generally should not do, but here this is an equality of integers, and all of these integers are divisible by d, so I could just divide by all of them. But now what does this say? This exactly now says that c over d times t is congruent to e over d mod, and so the only difference is now it's mod n over d. So this is just a small side note to handle the fact that sometimes I won't be able to just take the inverse of bt minus br mod p minus 1. And so what I have to do in that case is I have to divide all three of these terms by that GCD. And so in this case, I have to solve the equation bt minus br over d times k is congruent to ar minus at over d mod p minus 1 divided by d. And note now, the GCD of these two numbers is 1, because I divided out the GCD before, and so what I get is that k is now congruent to the inverse of this, mod p minus 1 over d, and by this I mean the integer. And so as a result, I will have found k mod not p minus 1, but mod p minus 1 over d. Now, you might rightly complain that this is not a very good answer, because I'm supposed to actually know what k is mod p minus 1, and this is not quite that. But as long as d is small, this only leaves a few possibilities, and I can just try them. So for example, if d is 2, and I'll show you an example of this in a minute, then that actually only leaves two possibilities for k. I could just try them. If this d is too big, it might leave lots of possibilities for k, in which case I might want to rerun the algorithm. Okay, so as before, I want to show you a computer running through this, and I'll show you what's going on with this d thing, because I think this makes it all seem more distressing and complicated than it actually is. So, unlike the previous factoring algorithm, this algorithm is actually going to take in three different inputs. So we need the prime that we're working mod, in this case 23, a primitive root mod that prime, in this case I'm going to choose 5, which is the smallest primitive root mod 23, and then the number I want the log of, so in this case I'm going to choose just 7. And I've programmed it to actually spit out for you basically the whole story of what happens with this equation. And so our collision here is that 5 to the 16th times 7 to the 5th is the same thing as 5 to the 20th times 7 to the 21st. Translating that to an equation mod 22, we get that 16 plus 5k is congruent to 20 plus 21k mod 22. And then this all simplifies to 6k is 4 mod 22. In this particular instance, you'll notice that everything in sight is divisible by 2, so we have to divide everything by 2, that's the GCD. So once we do that, then we end up with 3k is 2, now mod 11. Calculate the inverse of 3 mod 11, that happens to be 4, you can even do that one in your head actually. And then if we multiply both sides by 4, then we get that k is 8 mod 11. So let's summarize what we're doing. We want to solve 5 to the something is 7 mod 23. And as a result of this algorithm, I've learned something about k. Namely, I have learned that k is 8 mod 11. But we actually want k mod 22. I remember exponents mod 23 work themselves mod 22. And so what are the possibilities mod 22 for a number that's 8 mod 11? Well, there's actually only two of them. Namely, the two possibilities are, well, k is actually 8 mod 22, or k is actually 19 mod 22. And these, in fact, are the only possibilities. So note, even though we got this GCD, in this case that we had to divide through, we actually still narrowed this down to two possibilities. And once we have this narrowed down to two possibilities, we can just check them. So let's see, is the discrete log of 7 base 5 mod 23, is it 8? Well, it's not, because if you actually calculate that power, you don't get 7, you get 16. So, then is it 19? Aha, it is 19. So what we've calculated here at the end of all of this is that the discrete log of 7 to the base of 5 mod 23 is 19. Now, this algorithm has some randomness in it. So if I run it again, I hopefully won't get a different answer, because the log of 5 base 7 had better always be 19, because we've just checked that. But you can see here when I run this, I actually don't get any GCD between my coefficients. I just end up having to solve 9k is 17, mod 22. So I calculate the inverse of 9, it's 5, multiply both sides by that, and then I just go straight to k is 19. Now, of course, it wouldn't be very impressive if the biggest number I worked with here was 23. So let's jump up to a significantly larger prime, just so that you can see what this looks like in a more sophisticated case. So I'm going to jump up to the prime 10,007. So before I can even write down a problem, I first need to calculate a primitive root mod 10,007. And as you have likely discovered already, the command primitive_root gives you a primitive root. And so we see that mod 10,007, 5 is actually a primitive root. So let's actually ask the same thing. Let's ask what power of 5 is 7, mod now 10,007. As expected, it took longer for the rabbit to catch the turtle in this instance. It actually took 121 iterations, because again, we're working modulo a much larger prime. And I just want to emphasize that the output here is showing you what the path looks like. Namely, the path consists of our y values. So that is my mod p number. So the turtle and rabbit are both starting out on the first step, which in this case is 9,367. And they've recorded how that particular number is written in terms of a and b. Namely, what this is saying is that 5 to the 527th times 7 to the 4,515th is in fact identically equal to 9,367. Now, if we skip down a little later and just look at what's happening to the AB pairs, you can tell which of the three cases we ended up in. So, in fact, in this whole row that I have highlighted, you can see that in each instance, to go from one step to the next along the turtle part of the path, what happened is that we multiplied by g. In this case, we multiplied by 5. And you can see that because a is going up by 1 in each of these. From there to the next step, what's happened is that we've squared y. And you can see that because, again, both a and b doubled. And so what's really happening is this whole time, all along this path, a and b are bouncing all over the place. And as a and b are bouncing all over the place, the value of y is also bouncing all over the place. And we go along this path until we find this collision. Now, in this case, it actually happens that the y value that coincides is 26. That is, we have written 26 in two different ways. Now, again, I just want to emphasize, our fear here is that we'll end up writing 26 in the same way at two different points on the path. And that can happen, but it's fairly unlikely because of the fact that the A's and B's are basically bouncing around in a way that, again, simulates random. And so it's unlikely that my A's and B's wander back to the same place that they were to start. So that's why we have it ending up looking like this, whereas you see the A's and B's that the turtle and rabbit see are actually completely different, even though the number they see is the same. And that's the reason why this whole algorithm ends up working. Again, in this instance, I end up finding k not mod 10,007, but mod 5,003. And so we again have narrowed it down to two possibilities. Either the discrete log is 1,301, or it's 1,301 plus 5,003. Let's see which one it is. In this case, we're lucky on the first go. The discrete log of 7 base 5 mod 10,007 is 1,301. If we want to look at how this algorithm performs on some larger numbers, we can go ahead and here have Sage pick a random 10-digit prime, pick a primitive root, mod that, and then calculate the discrete log of some random thing, mod that number, and just see how it performs. Note in this particular instance, this GCD of the coefficients ended up being 72, which means that actually this one run through this algorithm narrows the k's I have to check down to 72 possibilities. Now, for a 10-digit number, checking 72 possibilities is not that bad, so even though this would be annoying to do by hand, in terms of the additional work that you'd have to do to go from here to a complete solution, it's actually pretty small. You can play with this again on your own and see. I think 10 to the 12th seems to be around the size where this gets upset. Also, it occasionally ends up throwing me an error, and I'm not exactly sure where that error is coming from. So if you want to play find what Tommy did wrong in this code, that somehow it magically works for smaller numbers, but then occasionally around 10 to the 12th, something blows up for reasons I can't fully wrap my head around, by all means, please do, and email me if you figure out what I typed that's wrong here. But running this a few times, you can see the GCD is usually somewhere in the vicinity 2, 4, 8, something like that. Sometimes you get as big as 72. You're pretty rarely going to end up with getting a GCD that's some enormous number. And as this program successfully goes about calculating discrete logs, mod 10 to the 12th, I again want to remind you, like we did with the trial division section, this is way, way past the place where you could do it with the naive algorithm of just trial and error through the various exponents until you find the discrete log. So what this is doing is actually quite impressive in terms of the scale of the question. Again, just like with factoring, I said, roughly speaking, Pollard row can factor numbers that are twice as many digits as trial division. The same is true here. Pollard row should be able to calculate discrete logs, mod primes, that are roughly twice as many digits as the primes for which you could just try the exponents until you got lucky. I'm going to wrap up our discussion of Pollard row here. Hopefully this Sage demonstration helps make this all feel real and makes it feel like you can really understand what these algorithms are doing, and in particular understand that even though the description is really weird, these algorithms really are much faster than the sort of naive alternatives. And in particular, the existence of these really weird algorithms should make you at least believe that plausibly there could be weird algorithms out there that we haven't found yet that do these problems even faster than the ones I've shown you here. And indeed, at least in the case of factoring, there are plenty of algorithms significantly faster than Pollard row, although, as we'll talk about later, they end up being a good deal more complicated. So this is as complicated as I'm going to talk about in this course, but if you're interested, at least one student is doing their final project on the quadratic sieve, so you'll get to learn some more about that then. Anyway, I'll wrap up this video here. Hopefully that helped, and I'll see you all in class.